Hey everyone, and welcome to today's Explainer. I am so thrilled to have you here. Look, our mission today is incredibly straightforward. We are going to build a simple, easy-to-memorize conceptual mind map of thermal physics and a really fascinating phenomenon called Brownian motion. We're going to take these complex physical laws, strip away the jargon, and break them down into plain English that actually sticks in your brain. So let's just dive right in.
Okay, before we get into the heavy science, I want you to picture a quiet room, early in the morning. Sunlight is streaming through the window, right? It creates that bright beam of light across the room. If you look closely at that sunbeam, you'll see tiny specks of dust dancing around in this totally random, chaotic, zigzag pattern. They literally never sit still, but why? There's no wind in the room, there are no tiny fans blowing them around. We're grounding ourselves in this highly relatable real-world mystery right now to kind of hook our curiosity today. Because honestly, understanding why that dust dances is the absolute key to understanding the invisible forces that govern our entire universe.
So here's the conceptual mind map we'll be building today. First, an intro to thermal physics. Second, macro versus microsystems. Third, the Brownian motion mystery. Fourth, Einstein's brilliant explanation. Fifth, a step-by-step mathematical proof. And sixth, the factors controlling the motion.
Let's start with Section 1, Intro to Thermal Physics. You know, what's really interesting about this textbook definition is how simple it actually is when we break it down. Thermal physics is exactly what it sounds like. The Greek word therm literally just means heat. So this is the branch of physics that studies the relationship between heat, work, temperature, and other forms of energy, like kinetic or mechanical energy. It's basically the science of how heat flows, how it changes the temperature of a system, and how we can actually convert that energy into useful work. Think about the engines in our cars or the air conditioners cooling our homes. That is thermal physics in action.
Moving on to Section 2, Macro versus Microsystems.
Okay, so here we have the crucial difference in scale. On the left side, we've got the macroscopic system. Macro just means large. This is a system containing billions of atoms or molecules, like a cylinder full of gas or simply a cup of water. And because it's so massive, it has properties we can easily and directly measure with everyday tools, like temperature, pressure, and volume. I mean, you can stick a thermometer in a cup of water and boom, you immediately get a reading. But on the right side, we have the microscopic system. Micro means small. Here, we're zooming way in to look at a single isolated atom or molecule. At this tiny scale, we care about entirely different properties, kinetic energy and momentum. And here's the kicker. You cannot directly measure the kinetic energy of a single atom with a standard tool. It's just not possible. We actually have to use special laws and theories to calculate it.
To really hammer home the sheer, mind-boggling scale of a macroscopic system, take a look at this number. 6.02 times 10 to the 23rd power. This is known as Avogadro's number. It represents the number of particles in just 1 mole of a substance. It is a massive, almost incomprehensible number of atoms, just a ridiculous amount of zeros. Because there are so many millions and billions of tiny particles zipping around, colliding and transferring energy, we can't possibly track every single one individually. That's exactly why we need thermal physics and statistical mechanics to make sense of all this massive chaos.
Which brings us to Section 3, the Brownian motion mystery.
All right, here is your easy-to-memorize definition. Brownian motion is the random and irregular zigzag motion of molecules in a fluid. And remember, in physics, a fluid can either be a liquid or a gas. It's that chaotic, completely unpredictable movement. It's exactly like the dust dancing in the sunbeam we talked about earlier, or imagine a speck of smoke just drifting aimlessly in the air.
Let's walk through this timeline to see how this whole mystery actually unfolded, because it's pretty funny. Back in 1827, a botanist named Robert Brown was looking at pollen grains suspended in water under his microscope. He noticed that these tiny particles of pollen were moving around erratically, zigzagging all over the place. Now, because he was a botanist who studied plants, he initially, and totally incorrectly, assumed that these pollen grains had some sort of life force in them. He thought they were literally alive and swimming around. But then he tested completely lifeless dust and sand particles and saw the exact same dancing motion. Well, the scientific community was completely baffled by this. For decades, scientists argued over why this happened. Some desperately tried to use it to prove that invisible atoms existed, while others completely rejected the idea altogether. It wasn't until 1905 that someone finally solved the puzzle.
And that brings us to Section 4, Einstein's brilliant explanation.
The scientist who finally figured this out was a 26-year-old Albert Einstein. The year 1905 is famously known as his miracle year, and one of the vital papers he published was actually on Brownian motion. Einstein realized that if the kinetic theory of matter was true,
Fluids were made of tiny, invisible atoms constantly vibrating and moving. He explained that a suspended particle like our pollen grain is constantly being bombarded by invisible water molecules from every possible direction. Now, usually these hits just cancel each other out, but by sheer mathematical probability, there are chance fluctuations. There are brief moments where, purely by random chance, more water molecules hit the left side of the pollen grain than the right side. And that unbalanced force is what physically pushes the pollen grain. A millisecond later, more molecules hit the bottom, pushing it up. And that right there is what creates that random zigzag path.
So let's lock in the crucial takeaways here. First, we have continuous collision from invisible fluid atoms. Second, those random collisions create an uneven force that constantly pushes the visible suspended particle around. And third, and guys, this is the most profound takeaway, this was the ultimate visible proof that invisible atoms actually exist and that they are in constant motion. Observing a visible speck of dust or piece of pollen dancing around under a microscope was the visual evidence the scientific community finally needed to accept that matter is in fact made of atoms.
Let's get into Section 5, the step-by-step mathematical proof.
I promise we'll keep this step-by-step and free of overwhelming jargon. Step 1. We start with the basic formula for momentum, which is P equals mass times velocity, or P equals mv. Step 2. According to the kinetic theory of gases, when these tiny particles collide, they perform perfectly elastic collisions. This simply means the transfer of momentum, P, is a constant value. Step 3. Now for some basic algebra. If we want to solve for velocity, or speed, we rearrange the equation by dividing both sides by mass. So we get v equals p over m. Velocity equals momentum divided by mass. Step 4. Notice where the mass is sitting in that equation. It's in the denominator. This mathematical proof shows an inverse relationship. If the mass of the suspended particle goes down, its velocity goes up. Mathematically speaking, a lighter, smaller particle is guaranteed to move faster when it gets hit by those invisible atoms.
And finally, Section 6, factors controlling the motion.
Okay, there are 3 crucial factors you want to memorize here that alter this chaotic motion. First is molecule size. The smaller the physical size of the particle, the faster its speed. Second is mass. Just like we literally just proved with our math equation, a lighter mass results in a higher speed and much greater randomness in its zigzag motion. A heavy particle just won't get pushed around nearly as easily. And third is viscosity. Viscosity is basically the internal friction or resistance of a fluid. Think of a really thick fluid with high viscosity, like honey, compared to a thin fluid with low viscosity, like water. A particle suspended in thick honey is going to face massive resistance and move very, very slowly, meaning a lot less Brownian motion. But in a thin fluid with lower viscosity, like water or the air around us, the motion is incredibly fast and chaotic.
We've built a really incredible conceptual map today, traveling all the way from the macroscopic world we can easily see, down to the microscopic collisions we can't. So I want to leave you with this final provocative thought to ponder. If the invisible, chaotic collisions of billions of tiny atoms literally have the power to make visible dust dance in a sunbeam, what other invisible forces are silently shaping the macroscopic world around us right now? Keep your curiosity focused, keep looking closely at the ordinary things around you, and I'll see you in the next explainer.